This job aid was produced by the National Weather Service Training Center to assist qualified NWS, DoD, and FAA electronics technicians in performing routine maintenance. This presentation will reference maintenance procedures from the relevant engineering handbook that was in use at the time of its production. The technician will refer to the most recent engineering handbook for current procedures, cautions, and warnings. Measurements captured in this video are from a non-operational site and should not be used for comparison to measurements at a field site.
Spectrum bandwidth measurement. Each radar has a license to operate at a single frequency. For a redundant site, you've got two frequencies that you operate at. This procedure verifies that we were within our bandwidth limits for those frequencies, that we're not taking up too much of the RF spectrum. This is done after we tune the klystron, as tuning the klystron affects our bandwidth. And we will be measuring in half bandwidths. In other words, we're going to measure above our site frequency and below our site frequency. We'll be meeting the requirements of the radar spectrum engineering criteria. This means that at our negative 40 dB half bandwidth, we'll be within 7.26 megahertz of our site frequency. And our negative dB half bandwidth will be within 72.6 megahertz of our site frequency. If your system has a spectrum filter on it, your limit is 22.94 megahertz at the negative 80 dB half bandwidth. The procedure in the engineering handbook is written for a HP 8560. If you're using a different spectrum analyzer, you will have to figure that one out. Most of this procedure is pushing buttons. I'm not going to bore you with reading you the buttons to push. It works real well to have one person reading the instructions while another person pushes the buttons and turns the dials. If you get mixed up in your button pushing or the sequence of the buttons, just turn the power off on the spectrum analyzer and start over. It's not that big a deal. Our initial conditions are that we're going to have control at the RDA site with the system in standby and breakers for the transmitter turned on. The test equipment configuration that you're going to put together in figure 5-15 is very similar to the one we did in the klystron tuning. The biggest difference is we're going to move our 0 to 11 dB attenuator from being in series with our crystal detector to put it in series with the 0 to 110 dB variable attenuator in series with the spectrum analyzer. Once you've got your test equipment configured as per figure 5-15, turn the power on the spectrum analyzer and give it a 45 seconds or so to come up to speed. And here's our spectrum analyzer we're going to use. It uses a cathode ray tube for the display. It did not have a VGA output like we were able to use in the oscilloscope videos. So unfortunately, my images will not be the best. That said, at the end of a sequence of button pushes, we do have images of what your screen should look like, and I hope they're helpful. First thing we're going to do is set our site frequency. Well, this spectrum analyzer knows where our center frequency is. Then we're going to set our span to 50 megahertz. We're going to set our reference level via the amplitude push button to 0 dB. We're going to select attenuation and set it to manual and set it for 10 dB. We're going to select our division setting and set it to 10 dB per division. We're going to go to our bandwidth menu and set our resolution of our bandwidth to 300 kilohertz. And we're going to set the video bandwidth to 300 kilohertz. We're going to set the trigger to free run and set our sweep to 5 seconds. Press trace, more, detector modes, and select detector positive peak. At this point, we want to set our variable attenuators to 28 dB total attenuation. We'll fine-tune this in step 3. And we'll start our transmitter by going to System Test Software. From the Control drop-down, select AMA Receiver Control. From the Test Source drop-down, select Klystron Output. Ensure your pulse width is set to shorten 1, and then set your PRF to Delta 5. Inject the signal. The transmitter should start operating. You should see a waveform on the spectrum analyzer. This waveform may be saturated, as in the left image on this screen. We're going to adjust our attenuator in 1 dB steps to get the displayed spectrum to peak out right along the top line, the top radical of our display. This will give us a better dynamic range and make it easier to make our measurements. Press Trace and max hold A. And now we're going to measure the negative 40 dB half bandwidth. You're going to press your peak search, press marker and marker delta. Then we're going to rotate our knob until we see the negative 40 dB point on the leading edge or slightly below negative 40. Make note of your delta marker frequency. And this is your lower half bandwidth at the negative 40 dB point. We'll play a video on this momentarily. Now that we've measured the lower half bandwidth, we'll rotate our knob to the upper side, or the upper half bandwidth. Do it the same way we just did. Come down to a negative 40 dB point and read your delta marker frequency. And now we'll show you a video of the negative 40 dB half bandwidth measurement. With our marker at our site frequency, we're going to rotate the knob to bring our marker down 4 divisions to negative 40 dB. And we'll zoom this in a little bit. Maybe it'll be a little easier to see. So we're going to come down to the negative 40 dB point. And once we're down to the negative 40 dB point, we'll read the delta marker value. The trailing edge of the negative 40 dB half bandwidth is done the same way. We'll bring our cursor, our marker, back through the center point, down to the negative 40 on the trailing edge. And read our delta marker value. And if both of these measurements are less than or equal to 7.26, we will proceed to step 9. We'll only do step 8 if we did not get the 7.26 megahertz. It's very rare the spectrum would not meet negative 40 dB half bandwidth measurements. I've been around this radar for about 28 years and I've never seen this, but it may happen. And if it does, they would have you retune your cavities a little bit to try to correct for this. Again, this is very rare. And if you do have to make this adjustment, you'll have to go back and remeasure it. And if this doesn't correct the problem, you would go back and look at the input to the tube. That would be your pulse shaper and or the RF generator 4A1 to see if they're putting a problem into the tube and you're measuring your problem out of the tube. Now it's time to measure the negative 80 dB half bandwidth. You'll press a few buttons and get a screen similar to what we're looking at on this image. At this point, we're going to remove 16 dB from the variable attenuator. So whatever you've got your variable attenuator set to right now, remove 16 dB from it. What this will do, it will saturate the pulse at the top. That's okay. The spectrum analyzer still knows where the center frequency is at. You may notice some spurs showing up on the screen. The spurs are most likely a byproduct of the spectrum analyzer itself. If the spurs are real and you change the attenuation going into your spectrum analyzer in 1 dB intervals, your spur would change by 1 dB at the same time. They would walk in step. 1 dB input change, 1 dB shown on the screen change. In this example, we're looking at a spur and we change the input attenuation by 1 dB. The divisions are 10 dB apiece. So you look at this and you can see 1 dB input change had nearly a 5 dB change in the spur. So this is an internal component. This is not a real transmitted RF frequency issue. At this point, we're going to measure the negative 80 dB half bandwidth. We'll do this the same way we did the negative 40. We're going to rotate our knob and come down the leading edge, or the lower half bandwidth. Bring it down till you get to a negative 64. We're going for our negative 80 dB point, and we've removed 6 dB of attenuation. So we're going for a negative 64 on the screen will give us our negative 80 dB measurement. We'll do that for the lower half bandwidth, and then we'll do the same thing for the upper half bandwidth. And we'll play a video here of measuring the negative 80 dB half bandwidth. With our marker at site frequency, we come down the leading edge till we get to a negative 64 dB. And we'll zoom this in a little bit, make it a little easier to see. Still a little bit difficult with this CRT. We're going to come down to the negative 64. Probably easier to read the display than it is to count radicals. And we're reading that we've got negative 10.3 megahertz on our leading edge. Now measuring on the trailing edge, we'll come back through our center frequency and come down the trailing edge again to a negative 64. It's very difficult to get right on 64. And we've zoomed in, and you can see that we are at a positive 13.7 megahertz. So this system is legal. At this point, we've measured the negative 40 dB half bandwidths, and we've measured the negative 80 dB half bandwidths. If these values are met and there's no real anomalous spurs, the procedure is complete. We're done. If we did not pass the negative 80 dB half bandwidth, we have some adjustments we can make. Steps 16, 17, 18 will have us make some adjustments to try to correct that negative 80 dB issue. If steps 16, 17, and 18 did not clear our issues up, the next few steps will check the input of the tube. It's possible that the pulse shaper or the RF generator are causing the problems. Very few people will be taking those steps. And if all is well, in step 33, we're going to go to our system test software and exit out of our system test software and either return the system to normal operation or bring it back to standby for the next step in the transmitter alignment process.